Right, okay, so we're going to have a look at some of the key formulas that you need for the representation and summary of data in S1. And this first little table here talks about mean and standard deviation, how to calculate them. Notice in this area we're using mean as x bar, standard deviation as this sigma here. Okay. There's three situations really that come up in S1. You've got raw data, so a list, or maybe a stem and leaf, in a frequency table, and this means you still know what all the bits of data are, but it's represented in a table, or in groups in a frequency table, and that's a bit harder. So if you've got raw data to find the mean, you're basically going to add everything up, divide by how many. Simple as that. Standard deviation, you've got these, quite a lot to do really. I always think of it, I mean, forget the square root for now. So you've got the mean of the squares, because you've summed up all the x squared values, divide by how many, and then you take off the square of the mean. That's the mean, just squared. Now that gives you variance, you're square rooting that to find standard deviation. Okay, when you're looking at a frequency table, obviously you've got a little bit more to do, and you might have to add up the frequency, so the sum of f to find out how many things you've got, and you have to have an fx column, and you've got to add up that column. You're probably used to doing this sort of stuff at GCSE. Okay. From a group frequency table, you've just got to find the midpoint first, and a good way to find the midpoint, add up the endpoints and divide by 2. Now remember, the endpoints, be careful, make sure they're like overlapping, so they might have to change slightly. Okay, so just make sure you're careful with that. Okay, so that's mean standard deviation. If you're looking at medians and the quartiles, both lower and upper, then basically you've got two situations. You've either got the raw data as a list, or in a frequency table stem and leaf, which is it's in a list anyway, it's just written slightly differently. So if you knew what all the bits of data is, in those situations you want to use the 4 pots method. Okay, you can use n+1/2 for median, but most people use the 4 pots method. Okay, if you're not sure about that, have a look at the rest of the KESMAS videos, and we'll go through that quite early on. I think it's video 1 or 2. Okay. If you don't know all the bits individually, so basically a group frequency table, the ones where you find midpoints and stuff like that, you don't know all the bits of data, then you have to use interpolation. Okay, if you want to know about that, watch the video on that, it's a really good one. Okay, and then finally, these don't often come up, cumulative frequency. You might get given one. If you want to find the median, it's a bit like GCSE, cumulative frequency stuff, you read off halfway. It's just a rough estimate, and then quarter way, 3/4 for these. Now this is really important. You never use pots and interpolation together. You either use pots method or use interpolation. And remember, just to find the median, it's halfway, and the quartile is quarter way or 3/4 way. So that's something that people make a mistake with. They use pots first and then use it on the interpolation. That's wrong. Okay, either use pots or interpolation, never both together. Okay, the last bit on this table, and this sheet I took from the start of the S1 revision guide, so you should all have a look at that if you haven't got it. This is it. Looking at skew. Okay. Now we've drawn skew here, so probably easy to look at a symmetrical distribution first. It's not skewed, and you've got mean, median, mode, all here in the middle. Okay. Box, what's nice is even distributed. Quote data there, and there. It's all the same apart. These distances here. Q2 minus Q1, well that's this here, isn't it? Q2 minus Q1, that's that gap, they're the same, those little gaps. The formula, they will always give you this, to ask you to work out. You don't have to remember this. You find the difference between mean and median, mean take median, and then you divide by standard deviation. There's a 3 in there, you don't really need to know why that is, but there is. If it's equal to 0, you're nicely perfectly symmetrical. If it's very close to it, you can say it's approximately symmetrical. Right, positive skew. That's like as if you took this symmetrical distribution and pulled it to the right. Some extra value, it's been pulled out to the right. I always think of it like that. It's pulled a few values in. So you've got some very high values. Okay, that makes the mean large, because the high values, when you add them all up, it's going to make an effect. Median, not going to be affected as much, and the mode shouldn't be affected that much either. So the mean is bigger than the median, that's the key bit there. And if they ask, like, comment on the skewness, your mean is bigger than the median, you can say that's positive skew. Graph looks like that. Box plot looks like this. Okay. Also, you can look at this gap here and this gap here. How they've written that down. Negative skew all the way around. Pull to the left, so mean is less than median, less than mode. Okay. And that's what the box plot will look like. Okay. Like I say, the kind of question here will be comment on the skewness. One thing to add, if you've got a symmetrical distribution, you want to be using mean and standard deviation because they take into account all the bits of data. Very common question is like, well, what should I use for this data? Should I use mean and standard deviation, or should I use median and say interquartile range? Well, you say, okay, well if it's symmetrical, I'll use all the data and we'll use the mean and standard deviation. If it's skewed, you want to use the median and the interquartile range because they're less affected by any extreme values or outliers, okay? Hopefully that'll help you answer the questions on these ones. Make sure you practice them before the exam. Right, okay, so we're going to have a look at a histogram question. Now there's quite a few questions on histograms they can ask you, and this one's one of the more common ones. So in this case, we're given a bit of information and it's about recording amount of time watching something. And we're told that in one of the classes, the frequency distribution was 20 to 29. Now be careful, that doesn't mean it's exactly 20 to 29, it could have been 19.5 to 29.5. Okay, we'll have to be careful and have a look later on to see if that's right. The frequency was 9 in there, and on the histogram, the height of the rectangle represented in this class was 3.6, and the width was 2. Right, okay, well I know in a minute I'm going to draw a diagram for that. Before we get on to that question, there's a bit of just those standard statsy kind of wordy bits. Give a reason to support the use of a histogram, and for this data, well you can either say that it's continuous data, or that it's in a group frequency table. Okay, that's what the mark scheme wants. Right, write down the underlying feature associated with each of the bars in the histogram. Well, if you remember back to the video Mr. Dawson in, this is probably stuck in your mind, that the area of the bars is proportional to the frequency. Okay, I've written that down there. That's the underlying feature. Right, now, we've got to show on this histogram that each trial was represented by 0.8 centimeters squared. So the first thing I drew a picture. We were told from 20 to 29. Well, I think that goes from 19.5 to 29.5, so we're a gap of 10. Okay, it might not be that, but that's what it's like on some questions. I don't think we have to use it on here. We just say it's 2 centimeters across, 3.6 tall. So I worked out the area by tying them together, 7.2. And that gave me a frequency of 9. And they're not the same. Area and frequency is not the same. They're proportional to each other. So I said, well, these 9 children here, that represented by 7.2 centimeters squared. So divided by 9 to get one child is 0.8 centimeters squared, and that's what it's after. Okay. What might happen now in a different question? They might say, oh, here's another group, and it might be half the size or twice the size. So you have to work out an area and work out what frequency it should be. They could ask something like that. Here they say the total area under the histogram was 24 centimeters squared. How many children in the group? Well, every child is represented by 0.8 centimeters squared, so I want to see how many children fit in, how many 0.8s fit in. So 24 divided by 0.8 gives me that 30 children. Okay. Other things they could do with histograms, they could get you to draw one. It's very rare, but they could do. Just remember, if you're doing that, you might want to work out frequency density, which is the height of your bars, and you do that by doing frequency divided by the class width. So in this case, class width was 10, so you divide by 10. Okay. Other ones, you could get a histogram, and they could ask for a small bit of information about it. And a lot of people make the mistake of just working out the area, just straight the area. But as we see here, that's not necessarily the frequency. So you might have to work out the area of all the bars, work out how many people you got in total, and you can work out what that kind of scale factor is, what the proportion, what the relationship is. Always draw a picture, always write on the diagrams that you do, you'll be easy.
Right, correlation and regression. I found quite a nice question because this one sort of combines the two in the same one, rather than me sort of showing you two different examples. Now, we just look at the question itself. We're given all of the raw data, so there's 8 bits, and we need to obviously read what the question is telling us. So the number of visitors in thousands, and the amount of money they spend in millions. They'll be important later. And we're given some other information as well. Always look at this first, because sometimes we can waste our time calculating some of these when actually we're given quite a lot. So we're actually given SVV, we're given SVM, SMM, we're given the sum of V and the sum of M. If we start the question, Part A says find the product moment correlation coefficient. Now, if we just move across to the formula book, we can see we've actually got all of the formula we need. Now, we are actually given these three in the question, but if we're asked to calculate them, we've got the formula here. Don't try and do it from memory. Have a look. Make sure you pull it out. Make sure you write it down carefully. And actually, then we've got the calculation for the PMCC right here. So in this case, we've got SXY, so we know for the question it's going to be SVM. And on the bottom, SXX and SYY, we know it's going to be SVV and SMM from the question itself. And I've got all three of those here. So part A, all I've done is take those three and sub in the three values they're given. As I said before, you may be able to have to calculate these. Make sure you do that accurately. And we get at the bottom 0.962. And that's all we were asked for. I've written it to 3 sig fig. We may be asked to go a little bit more accurate. Now what that tells us is that there's high positive correlation. 1 would be perfect positive correlation. -1 would be perfect negative. And this telling us pretty close to 1. So it helps me with part B. Because part B says give a reason to support fitting a regression model, i.e. a straight line of the form M equals A plus BV to this data. Well, considering the correlation is so high, they're almost a straight line, so it definitely supports it. And that's what I've written. Move on to part C. Find the value of B. So we've done the correlation, that's high. Part C, it says calculate the value of B. Now if we look at the line M equals A plus BV, B is our gradient. And back to the formula book, B can be calculated by SXY over SXX. Now we've got to be a little bit careful here because we're using different letters. So SXY we know is going to be SMV. Now the mistake that is made is at the bottom, SXX. Now if we look at the line, we're used to seeing Y equals A plus BX, so that means that X has been replaced with V, so we need SVV, and that's what I've written here. So our gradient is SMV over SVV. Plug it in, we get it to 3 decimal places. Now you'll also see that I've written it slightly more accurately a line above, because I'm going to use that ideally, leave it on your calculator. On the next part. Now D, find the equation of the regression line. So now we need to find A as well. Rearranging this gives me A is M minus BV, and we know the regression line has to go through the two means. So the mean of M and the mean of V. Now we're given the sum of V and the sum of M, and we know there's 8 values, we can easily get the two means. And all I've then subbed in is my value of B, but my more accurate value of B. That's key. Okay? And that gives me my value of A as minus 467.1969, which I've also put to 3 significant figures, giving me my regression line. Very nice. And as long as you're clear, as long as you're careful, you shouldn't be getting that wrong. If we move on to part E, very, very common, interpret the value of B. That's our gradient. So it's this here. Now if I go back to the question, my gradient tells me that every one I go across is how far I'm going to go up or down if I think about it from a graph. So V would be my x-axis. So for every one I go across, but it's not one. Because it's in thousands of visitors, it's actually for every 1,000 visitors. It will tell me how many millions of pounds I've spent. That's sort of my one across and how far up I go. So, for every 1,000 visitors, I'm going to have 0.740 million. And now I decided to write that, instead of 0.74 million, I've decided to write that as 740,000. So for every 1,000 visitors, it generates 740,000 from what they spend. Okay, as long as you read it carefully and think about what the gradient means, that should be a straightforward 2 marks. They'll sometimes say to look at A as well. It doesn't in this question, but if I was to think about what that A meant, that's basically telling me if V is 0, Now V was the number of visitors, so we have no visitors, it would be the amount of money they spent. That wouldn't make a huge amount of sense in this question, but you could be asked that in a different one. So just bear in mind what A means, that intercept on the y-axis. Right, we carry on moving down. So F, use your answer in part D to estimate the amount of money spent when the number of visitors is 2.5 million. Got to be a little bit careful, because if you see, all I've done is substituted into my regression line, but I've not substituted in 2.5 million, because I need to sub in V in terms of thousands of visitors. So it'll be 2,500,000 visitors, so therefore I'm only going to sub in 2,500, which comes out at 1383, and again that's in millions, so therefore it's going to be £1,383,000,000. Pretty large number. Then part G, comment on the reliability, again quite a common question, of this answer. Now if I look at what I'm substituting in, and then look at my table, I can see that 2,500 is within the range of my data. My lowest is, 2290, and I go up to over 2,500. So I'm pretty confident that's going to be reliable because it's within that range, and that's what I've said. If it's outside of that range, it would be called extrapolation, very unreliable. So I'm pretty happy with that. All in all, questions you can easily get full marks on. Practice them. Every single paper will have one. Okay? Stick it in your mind.
So I want to go through a couple of the rules that you need for probability, and you will find some of these in the formula booklet. So like this first one here, probability of A or B, probability of A, probability of B, take probability of A and B. Now that's given the formula booklet, but you can rearrange that. So if you've got any three of these, you can work out the fourth one. Okay. And then this one, the given formula, and it's given like this in the book, similar to this in the formula booklet. But I remember it like this: probability of A given B. Probability of A and B, so the same two letters, just intersection and instead of the given line, out of what's been given, to the bit on the end. Okay? Right. Now there's some special formulas you can use in certain cases, and people get confused with these, right? So mutually exclusive, that's the probability of A and B is 0, okay? And that's when they're separate like this. Now an independent, they were not separate like that, they could intersect, but what's important is how much they intersect by, okay? And you find out how much they intersect by probability of A and B, probability of A times probability of B. That only works if they're independent. Or this one here, probability of A is the same as probability of A given B. And that makes sense to me because what that means is, probability of A, given that B's happened, hasn't changed from what it was beforehand, just on its own. So it's independent of B. Okay, so that makes sense to me. So remember, mutually exclusive looks like that. Probability of A and B is 0. If they're independent, you test with either one of these rules, and they will overlap, but just this tells you by how much they overlap. Okay, hope that's clear.
Okay, this is Tree Diagrams 101. We've got this exam question that says a disease is known to be present in 2% of the population. A test is developed to determine whether someone's got it or not. Given that a person has the disease, the test is positive with probability 0.95. Given that they don't have the disease, they've still got a 0.03 of a false positive. And they want us to draw that on a tree diagram. So all I do is split that into my two events. Event number one is, do they have the disease? I know that 2% have it, so its probability of disease is 0.02. And if that's true, then 98% don't. So D complement, not having it, is 0.98. Event number two is whether or not they test positive. So, given that they have the disease, they've got a 0.95 chance of testing positive. So positive complement, not getting a negative, is 0.05. Same deal. Don't know if you can read here. It tells us that if they don't have the disease, they've still got a 0.03 chance of testing positive. So in all likelihood, if they're probably going to test negative. P complement is 0.97. Now I've added on to there to help myself answer the other questions, the outcomes, disease and positive, disease and not positive, not having the disease and getting a positive, not having the disease and not getting a positive. And it may or may not be useful, but it only takes a second. We work out the probabilities of each of these outcomes by timesing along. Remember that from your GCSE, you times along a branch. So I did that, put my probabilities on of each outcome happening. So I read on and I see a person is selected at random from the population and they're tested for the disease. Find the probability that the test is positive. Well, for part A, I'm looking and I've got a positive result here. That's having the disease and testing positive. And I've got a positive result here. That's not having the disease and testing positive. So if I've got more than one possible outcome that matches the criteria, I just add them. So you can see here, for part B, I've got probability of positive, I've just added the two together, 0.019 plus 0.0294, giving me a total of 0.0484 for testing positive. Simple as that. Then it says, a doctor randomly selects a person from the population and tests him for the disease. Given that the test is positive, so we know they've tested positive, find the probability that he does not have the disease. So for part C, we know that it's positive, so it's only going to be out of these two values. That is my denominator. I'm doing a given question and I can see it's out of the people who've tested positive, which we worked out in part B as 0.0484. So it's out of those people. What is the probability that he doesn't have the disease? So we're looking at these folks, so it's this out of both of these. So I just look at the diagram, I identify that it's the people not having the disease out of the people who test positive. Simple as that. Probability of not having the disease given that they've tested positive. Alright, and that's 0.06007 something, so 0.0607 to 3SF. Simple as that. Now it does say, there's a part D here, it says comment on the usefulness of this test. Well, all it's asking you to do is show you understand the numbers. We've just shown that if you test positive, you're over 60% likely not to have the disease. So given that they're trying to find people and treat them, it's probably not that useful a test, because even if you test positive, the chances are you don't have the disease. Enjoy your tree diagram questions.
Okay, so I'm just going to have a look at a question on Venn diagrams. So we've got a few bits to start with. Explain what you understand by a sample space and event. These are quite specific definitions, so I wrote them down in full here so you can see what they are. So we've got a sample space, a diagram, or it can be a list, something that represents all the possible outcomes, okay? So you quite often see these as like, you're probably used to the tables, where you can fill in with like dice events and stuff like that. It's a sample space. An event is something which happens, which is one or more outcomes, and it's a subset of all outcomes. Right, okay, so you could say, well, an event is basically something that's happened. So rolling the dice, the event's rolling the dice. The outcome is what 1 to 6 could be. Okay, and that's the official bit. I took that straight from a mark scheme, so that's a good one to do. Right, okay then, so let's go back onto the actual question then. So we're given events A and B, so probability of A is this, probability of A is this, probability of A given not B. Bit of a weird one to give us that, but we'll deal with it. Now what I did, I wrote down all the things I know. So probability of A, not B, not B, and this weird one here. And we've got quite a few individual bits to work out. So probability of A and not B. And I said, well, that's very similar to this here. So I think using a formula relating given to this would be useful. Okay, and this is what here. So I always remember probability of A given B, probability of A and B, not B in this case, we're looking at not B with a little dash on. So it's the A and the not B, A and the not B, but this is and given. And then it's out of what's been given. So out of not probability of not B. Try and remember that. It is written down in the exam, but in a slightly different form. Okay. And all I've done there, I've plugged in what I know. So I know this, it was given. So I put that in. Probability of A and not B, I don't know, that's what I'm after. And then a half is probability of not B. Okay. So then I just times by a half. Half of 4/5 is 2/5, and there's our answer there. Okay. Right, the next bit's quite a strange one. It says, find the probability of A and B. Okay. Well, this one's a bit strange. So I tried to draw a diagram. So I've got A and B, and then I've got A and B, and I've put on probability of A is 2/5, and that's this whole area there, whole of A, right? And then I tried to draw the probability of A and not B. So I want A and not in B, so it's just this like moony shape here. Now that's 2/5 as well. And I thought, well, hang on a minute, how can this area and this area be the same? Well, it's only if that intersection is 0. So probability of A and B is 0. Okay. That means it's mutually exclusive. Alright? And I think that's a later question later on. This diagram's wrong. They should be separate and not overlapping. Okay. So try and draw a picture if you can for these. It makes things much easier. Right, and then we're looking at probability of A or B. So we've got another formula for that. For A or B, probability of A plus probability of B, take probability of A and B. Now you can rearrange this how you want. We just put in what we've just found out. Probability of A and B that is 0 and the 2 probabilities to start with. And we get 9/10, easy enough. Then probability of A given B, I think the next one is. Yeah. So probability of A given B, all I've said is probability of A and B over probability of what's been given B. It's the same pattern as before. Well, probability of A and B is 0, so it doesn't matter if you divide it by half, it's still 0. Probability of A and B is 0. And then we've got a comment on if it's mutually exclusive, if it's independent. And this is where people go wrong quite a lot. Mutually exclusive, we know that because there's no intersection, probability of A and B is 0. Okay. Now there's two ways to check if something is independent. Just for the last bit. Probability of A is 2/5. Now if it's independent, it wouldn't matter that B's happened. Probability of A should stay the same. So the probability of A given that B's happened should still stay the same as 2/5. In this case, it changes. That means B's affected it. So they're not independent of each other. Okay. So in this case, they're mutually exclusive. They're not independent. You can check by doing is the probability of A times probability of B over the probability of A and B, and you'll see that won't work either. And I'll mention that in another video, as you probably should have already seen. Right, okay. I'm just going to go through this question on Venn diagrams. This is a slightly easier question. So, if you ever see they start giving you a list of like, oh, there's 100 people, somebody did this, somebody did this, somebody did this, lots of numbers. If you just see it be a two-way table, I recommend doing a Venn diagram for this, and you are given a Venn diagram. Because there's three things, Venn diagrams lend themselves this perfectly. So we've got three things that are happening. We've got people wearing glasses, people left-handed and dark hair. So I'll put glasses, left-handed and dark hair. And the best way to work is work backwards. You work from the inside out. So I start here at the end. It says, right, only 10 people wore glasses, were left-handed and had dark hair. That's all three. So I put 10 in all three, right in the middle there. And that'll overlap of all three. Right, 15 were left-handed and dark hair. Oh, left-handed and dark hair. So this overlap here. Well, there should be 15 in this whole segment. I've got 10 already there, so there should be 5 there, making 15 altogether. Go backwards again. There's 19 who wore glasses and had dark hair. Glasses and dark hair, so this overlap. Got the 10, so 9 more there. Go backwards again. 17 wore glasses and left-handed, so you see we've done the similar thing there, making that add up to 17. Right then, going back to the next bit. 36 had dark hair. Okay, well I've got the 5, the 10 and the 9. Add them up. Take them off 36, there's 12 left. Done. 28 people left-handed, same thing, should be 28 in this circle. I've got 5, 10 and 7, so that gives me 6 left to make that up to 28. You've got a calculator to check this as well. And finally, glasses also had 36, so add them, take them off 36, there's 10 left there. Don't forget about the 41 around the outside, because there should be 100 altogether, so I add everything up, take it off 100, I get 41. Okay, now if you've done that right, this should be easy to do the next part of the question. Okay. So what we're looking at is find the probability person wore glasses, was not left-handed and did not have dark hair. So if they wore glasses, not left-handed, not dark hair. So I think we're looking in this area here. Okay, just this 10 bit there. Okay. So I reckon that is going to be 10 out of the 100. Right, okay, well I'll cancel that down to 1/10, fair enough. Okay then, notice I'm doing this without a calculator. Check on the calculator if you've got some more complex things here. Right, did not wear glasses, was not left-handed, and did not have dark hair. Alright, so it's what we worked out on the outside, so 41 out of 100. I don't think that would cancel down. Right, I had only 2 of the attributes. Okay, right, so I can't have this centre one because that's all 3. I can't have that single, 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 none. It's these bits here, only 2 of them. So I had 9 and 5 and 7, which should give me 21. So I get 21 out of 100. Okay, doing really well. Now there's a word here, they've whacked out a given. So we're going to work out if they wore glasses given that were left-handed and had dark hair. Well, I'm looking at, given they got the left-handed and had dark hair, well, where's that? Left-handed and dark hair is this overlap here. So I'm only looking at 15 people. Out of those 15 people, how many wore glasses? 10 did. So I'll say it's 10 out of the 15, or 2/3. Okay, be careful those given. That restricts what you look at. We're not out of the 100, we're looking out of what they tell me here. Left-handed and dark hair, 15. Okay. There are lots of different variations of Venn diagram questions. This one, the nice easy ones, diff comes up. You can do a little dance in the exam and walk out singing.
Right, so let's have a look at discrete random variables. So we're given our probability distribution and we've got 2 unknowns in this. Probability that x is 2 is p, probability that x is 4 is q. We're told that given that the expected value of x is 3.5, write down 2 equations involving p and q. Well, you've known for years that the probability of all the possible outcomes adds up to 1. So I've done that there, and so if you rearrange that, then you get p plus q must be 0.4. However, on the other hand, we know the expected value is 3.5, and to work that out, we do the value times the probability, do that for each one, and add it up. So we get 1 times 0.1, 2 times p, and so on. And then I've collected to work those out and rearranged it to get 2p plus 4q equals 1.3. Now the reason I knew to do that is because in part B it says find the value of p and the value of q. We've got 2 equations and 2 unknowns, and if that doesn't scream simultaneous equations at you, nothing will. So solve simultaneously, which I've chosen to do by multiplying the top one by 2 and then subtracting the top one from the bottom one. So I've got 2q is 0.5 and q is 0.25, and I've chosen to substitute that back into here to find p, which is 0.15. If you're unsure that you've got it right, you want an extra check, you could substitute both into the other equation and check it works there as well, but this is definitely right. So that's part A and B done. Part C. So this capital F, this means we want to look at the cumulative probability, and so what that means is f of 2.3 means the probability of everything up to and including 2.3. Well, remember this is discrete, and so what values do we have up to 2.3? Well, we only have the 1 and the 2. So really this is the same as saying what is the probability that x is less than or equal to 2? Well, that's just those 2 probabilities added together. We know that p is 0.15, it's 0.1, add 0.15 is 0.25. D, the variance of x. So, our formula for the variance of x is the expected value of x squared minus the expected value all squared. So we already know this, we're told it's 3.5, so we need to work out the expected value of x squared. Now to do that, we just square our x values before multiplying by the probability. Only square the x values, not the probabilities as well. Okay, so I've done 1 squared times 0.1, 2 squared times p, which is 0.15, 3 squared times 0.2, and so on. When you put that in your calculator, you get 14. So the variance is 14 minus 3.5 squared, and that comes out as 1.75. The last part. So it asks us to find the variance of 3 minus 2x. Now, this is going to be associated to this. And we want to know the relationship between the variance of this discrete random variable and this one. Well, adding this 3, because this is a measure of spread, doesn't change how spread out the data is. Multiplying each piece of data by minus 2 will have an effect. And because it's the variance, we've still got our squares in our formulas, then What we're going to do is we're going to take that -2, square it, and that's what gets multiplied by the variance of x. Okay, so we're going to square that -2, and it's that times the variance of x. We know the variance of x is 1.75, we know -2 squared is 4, so 4 times 1.75 is 7.
Alright ladies and gents, so we're going to look at your 1 minute quick stop shot for normal distribution, and this is how it works. We should recognise this as our distribution, and because it's symmetrical about the mean and median and mode, we can use this simple idea. When we have a value, we want to turn it into this distribution that has 0.5 of its median, so that's our z distribution. So to plug, we take our value, we plug it into this formula, z equals our value, take away the mean, divided by the standard deviation. To quote Mr. Dawson, fix it in your mind. That is your key formula. Your z value equals your x value, take away the mean, divided by the standard deviation. Once you've got that value, you just plug it into your table and it gives you the probability you want. Now they might try and trick you by giving you the probability and asking you to work out one of these three values. Well, then you just work backwards. You take your probability, you put it into your table, that gives you your z value. You take your z value and put it equal to your formula, and that will give you whichever value they haven't told you that they want you to work out, either x, the mean, or the standard deviation. So just working forwards, take x, put it through the formula into the table to get your probability, or working backwards, take the probability, put it into the table to get your z value and set that equal to the formula to work out the missing bit. Now when I say the table, this is what we're talking about, yeah? We've got the normal distribution function, all our z values with the probabilities next to them. Now this is the less than or equal to, this is the greater than or equal to. Don't stress too much about it. This is your first stop. If you can't find your z value in this one, check the little table out. Now, follow me. Alright, so in this exam question, we've got this scientist. He's finding that the time taken m to carry out an experiment can be modelled by a normal distribution, well, a normal random variable, normal distribution. Its mean is 155, that's key information, and standard deviation is 3.5, that's our other key information. So in part A, it just says find the probability that m is bigger than 160. Now you are an absolute muppet if you do not draw sketches for the normal distribution. Winners draw sketches. I've put it down here, I've got my mean at 155, 160 is bigger than it, it's asking me to find this green area here. So I know that my table, we mentioned the table, is the less than values. So all I'm going to do, I know probabilities add up to 1, I'm going to find the probability it's less than 160 and do 1 minus that. If I take away this bit, I'm left with the bit I want. So I'm going to actually work out the probability it's less than. So the probability m is less than 160. I take my value for m, I plug it into my formula, 160 minus the mean over the standard deviation gives me my z value. And to the nearest 2 decimal places, that's 1.43. So I take 160, put it into the formula, get my z value, put that into the table, and now I want 1 minus this probability, so I put that into the table and I get 0.9236. Take my z value, put it in the table, take the probability, I've got my answer. Boom. Easy as that. So 1 minus the probability it's less than 160 is 0.0764. Now part B, they said what's the probability it's between 150 and 157. If you're not a winner and you don't draw a sketch, it's really easy to get tripped up here. But if you draw a sketch, it's simple. The mean is 155, it wants the bit between 150 and 157. So all I'm going to do is find the probability that it's less than 157, all of this bit, and I'm going to take away from that the probability that it's less than 150. Alright? Now, I'm on the left side, so I'm actually going to use the symmetry to the probability that it's greater than 160. which is excellent because we've already worked that out over here. So I'm going to take my value from that, which is 0.0764. That's the probability that it's greater than 160, therefore the probability it's less than 150. Use that feature of symmetry. And I'm going to take that away from the probability it's less than 157. I take my value for m, I put it into my formula, I use my z value into the table, gives me 0.7157. So my probability that it's between those values is this probability, take away this probability, and that leaves me 0.6393. If you draw your sketches, follow the flowchart, it's symbols. Boom. Okay, part 6 says the value of m to one decimal place such that the probability of m being less than or equal to m is 0.3. Now, quick aside before we get into this, we know as brilliant mathematicians we don't need to worry about that inequality being equals or not to. It's the one time in life you don't have to worry about it, it's continuous, so it's irrelevant, it's just less than m. So this is just like the other questions, but instead of working forwards like we usually do, we're going to work backwards like we talked about. So I'm going to take my probability of 0.3 and I'm going to put it into the table to find my z value. Now, this is the nearest thing it gets to tricky in this. You'll notice that the probability, well, it doesn't have it here. So, probability goes down to 0.5 because that's half the distribution when the mean is 0. So what that means is we've got to use the little table. So the little table, we've got 0.3, z value of 0.5244. Now we're not going to get worried by that, but this is the nearest it gets to tricky if we're following the method. All we know is that the little table is greater than, so it means that bit, but we want the probability of less than, so using symmetry I reflect it. It's instead of 0.5244 from the table, it's just minus 0.5244. So this is my value here, minus 0.5244. So I've taken my probability, put it into the table, this time the little one, take my z value, put it into the formula. So z equals our value of m minus the mean divided by the standard deviation. Times by 3.5, add 155, my value of m is 153.1646, but wait, we need to answer the question. It says to one decimal place, so all I'm going to do is round that off as m equals 153.2. Barker out.
Mr. Dawson, year 12, we've got stats tomorrow morning. Any advice for them?
They've got stats tomorrow.
Yeah.
Not next week.
Oh, I think it's tomorrow.
I thought it was Tuesday. Smash it, it's easy. You've had loads of time since C2. Should have been 20, 30, 40 stats papers. Should walk in tomorrow. Blitz it. Good luck.
Stats. If you have to draw Venn diagrams, make sure you put a box around it. You'll lose a mark if you don't.
Mr. Jenner, have you got any advice for anyone taking their stats exam tomorrow?
Check your work carefully. It's easy to make a mistake with all the calculations.
Boom. Any other bits of wisdom?
Have a good night's sleep. Relax, do your best. The PMCC is unaffected by coding.
Keep calm, read the question, underline it, and remember winners draw sketches.
General advice for exams, sir?
Well, this stage, the work's done, isn't it? Just try to relax and enjoy it. Check your working as well.
Mr. Yaz, the year 12 have got their stats exam tomorrow. Have you got any advice for them?
Yes, make sure you don't forget any equipment. Make sure you bring your scientific calculator and good preparation. Not good luck, good preparation. I wish you all the best and be early tomorrow morning. Bye-bye.